Welcome back to the channel, everybody, and this is Deeper into Maths. And now we are going deeper into what diffraction is. Earlier, we had studied about a YDSC experiment, and it was pretty fun. And we derived many formulas that we thought we could never derive. For me, it was like that, and it was revolutionary. So now the scientist came to a thought that if we are using double slits, why not use a single slit and try the experiment once again? And so they did, and they got some extremely new results which are common now, but at that time they were revolutionary and mind blowing. So let us understand what those results were and what all did happen. So, what is diffraction? So diffraction is just the bending of a light around the edge of an obstacle towards an obstacle. So if you assume, I'll write over here the thought process, and over here I'll draw the reality so as for you to understand. So here is our small slit. Now we can say it's not a slit, it is a comparatively bigger hole that we have digged into a cardboard, and we are passing light through it. So let the light color be green, and we are passing light through it. Yes, we are passing light through it, and what was found was that all this light, the thought process was that the light should get obstructed over here, all this light, and the light in between must only be able to pass, and so there must be a bright spot that is of equal length, same as that of hole. I'll write over here, same as that. But this is not what happened. So what actually happened was that when we made a small hole and we passed light through it like this, it did not only go in this manner, but it also bended like this. Okay, that was an exaggeration at this point, and like this. And so the hole grew bigger and bigger, and the size of the hole increased. The final image of the hole. So, in order to answer this question once again, we go back to our theory of constructive and destructive interference, which we studied in waves. And we will answer this question once again by waves and not by a straight line, well, wave, that a ray that moves in a straight line. So, how did we understand it? The explanation. So let us take this once again. I'll redraw the diagram, and we'll not go into depth of it because the explanation is actually a very much longer than, because the conditions are very simple to remember. They are just like YDSC but flipped, as we studied in the thin film wala and like that things. So A and D, this is our screen, and here is our light source. So now what is happening is that there are infinite number of light sources over here. I'll write it with another color. Infinite light sources. in YDSC, there were only two slits and they were very, very small as we wrote the condition. So the small meant that only one light source was formed at a particular slit. But now that the slit width is increased tremendously in comparison to that width, now there are infinite number of light sources, and so they would make constructive and destructive interference all according to them. So well, the thing that we found that in diffraction, I'll use the yellow for heading, the constructive interference the path difference is equal to 2n plus 1 lamp by 2, and the path difference is equals to 2n plus 1 times pi, and the destructive interference the path difference is n lambda, while the phase difference is 2n pi. And this is the experimental results that we got, and that's just it. So we can't just get some explanation. You can actually get an explanation upon this on how this happens, but it's pretty complex at this level, so it's easier to learn this formulas. So let us understand where the first dark occurs. So we'll write A sine theta is equals to n lambda. By construction, we'll draw 2 points. Oh yeah, this is our this is our center point. And from here y, and we'll write it equals to n lambda. Let this be theta. So A tan theta equals to n lambda, therefore A, and the tan theta is opposite side, that is again tan theta is opposite, that is y, upon adjacent, that is d. Y upon d equals to n times lambda, therefore y is equals to n lambda capital D upon A. So for y, so this is our y of dark, right? D y dark first, therefore we put n equal to 1. So yeah, we start like that, 1 2 3 and so on, equals to lambda d by A. And the first dark, we got this, and the intensity of fringes, there's this huge formula, I equals to I naught into sine of beta by 2 upon beta by 2 the whole square, where beta by 2 is equal to pi a sine theta upon lamb. This is a very useful result, and there have been some amount of direct questions asked on it, which are like uh, the other things are constant and only sine theta is changed or the lambda is changed, and they are asked about the intensity. So we need to know a little bit about this formula in order to solve. And yes, so now let us get the bright fringe condition. So the bright fringes again a sine theta, as we write, plus 1 lambda by 2 ay by d equals to 2n plus 1 times lambda by 2. Then y bright equals to 2n plus 1 by 2 lambda capital D upon small a. This has been the formula. Yes, it's a pretty important result once again. And now over here the important thing to remember is that n starts from 1. We do not take 0 as we take in the YDSC. That's because I'll come in a short minute and explain the intensity of fringes. Let's start with that now. Intensity of fringes. Yes. So the intensity graph of the fringe is something like this. Experimental graph it is. So this is our y, and over here is our intensity. So I'm plotting the graph. The graph goes something like this. And it goes once again mirroring. I'll redraw it. And it goes and decreases till 0. So the brightest fringe is our central bright, and the width of central bright is twice the normal width. So width of central bright is equals to 2 lambda d by d. This is found by experiment. This is where we bisect the graph. So, and others have the constant width, have constant width of lambda d by small d. Yes. And you see the intensity goes on decreasing, and this is from this formula that I just made you write. This formula very important, and according to this, if we put the values, it goes on decreasing and decreasing slowly and gradually. Yes. And now the last thing to note is the validity of ray optics. Yes, ray optics. Now, how is ray optics introduced in between? So the scientists found about the dual nature of light, that it is again a particle. In some situations it's behaving like a particle, while in some situations it's behaving like a light. So wherein to consider it as a wave and wherein to consider it as a particle. So they found the validity of ray optics. So ray optics is valid up till the distance ZF, that is they call it as the Fresnel distance ZF, and the formula for ZF, that is the experimental formula that they found by experimentation, is that ZF equals to a square upon lambda. This is a very simple but yet effective formula, because sometimes we may get confused, and wherein a, here a is the distance width of slit, or we can say the size of slit. This is it then, and now we have covered the things important in the part discussion of the diffraction. In the next episode, we'll be studying about the practical applications of ray optics as well as combined wave optics, and we'll be understanding about the optical instruments that are used in our day-to-day life. So yes, meet you in the next episode.